Okay, today's video is going to be dealing with the first and second derivative tests. And what these tests are going to do is they're going to give us information about relative maximum and minimum values of functions. So for especially this first derivative test, all we're really doing in these notes, we're not really learning anything new, but we're kind of formalizing what we already talked about during our graph sketching and analyzing f prime work. We already talked about these ideas there. We're just kind of formalizing them into this test. So here's what the first derivative test looks like. The idea here is that if f prime changes sign from positive to negative at some value c, then f has a local max at value c. Right? And we already knew that when we were looking at the graph of f prime, we knew that in order to find a maximum value, we had to see where f prime changed from positive to negative. So graphically, right, what we're looking at is something like this. So let's say this is my graph of f prime, right, and I have a value c here, right? I know that on this section here, let me get some colors. On this part, I know that f prime is greater than 0. So excuse me, this is actually, if this is my graph of f. Right, so maybe I'll put that here. So if I'm looking at a graph of f, I know that if f prime changes from greater than 0, because my slope is positive, over here f prime is less than 0. So I know that where it changes from positive to negative, I have a local max at that value. Right, we could also consider a graph that looks like this. And so here's my point C. In this case, f prime of c is not 0, it's undefined, but we still have a similar situation. On this piece of the graph, f prime is greater than 0. And on this piece, my f prime is less than 0. But again, since f prime changed from positive to negative, I have a local max at c. So on the flip side, again, we already knew this. If f prime changes sign from negative to positive, then we have a local minimum at c. So that could look like this. Here's my graph of f. Here's my point c. And now, on this piece of the curve, f prime is less than 0 because I have a negative slope. Here my derivative is greater than 0 because I have a positive slope, and where I change from negative to positive, I have a local minimum value. Now the last piece of this says is f prime does not change sign at c, then f does not have a maximum or a minimum value at c. And that might look something like this. So my curve could flatten out. Right, so here we could flatten out at c, so my derivative is still positive, but since that's increasing everywhere, my derivative is positive everywhere, I don't have a max or a min value at c. So again, that's all the first derivative test is telling us, and again, that's something we really already knew. But we'll look at how we're going to apply it now that we know this test. So the note down here says using the first derivative test will not identify absolute max or min values, so we would still need to find the y values of the function in order to find those absolute extrema. So here's what these problems are going to look like. And again, we've really already done this work, we just didn't call it the first derivative test. So it says for each of the following functions, use the first derivative test to find out the local extreme values. We're going to identify any absolute values, and then we're going to justify. And really that's the new piece here. It's not just finding where those values are, but justifying them using this test. So if I'm finding extreme values, again, I know I have to work with my derivative, so I'm going to calculate my derivative here. So I get 3x squared minus 12, and I want to find out where that's equal to 0. So if I factor out a 3, I get x squared minus 4. That's equal to 0. And so now I know this is x minus 2 and x plus 2. So I have x equals negative 2 and positive 2 are my critical points. So just like before, we're going to do our little table here. So we're looking at f prime of x And I'm going from negative infinity, negative 2, positive 2, and infinity. And I'm just going to test in each of those intervals to find out if I'm positive or negative. So if I plug in a negative 3, that's going to give me a negative here, also a negative here, so I'm going to be positive over that interval. F is increasing. Between negative 2 and 2, I'm just going to pick 0, so I'd have a negative times a positive, which is going to give me a negative for that interval. And then something greater than 2, say 3, I'm going to get positive times a positive, and so I'm going to be positive there. So now I know that my function is going to have a local max at x equals negative 2. So f of x has a local max at x equals negative 2. And again, that's not new. We already knew how to do that before from our graph sketching and analyzing f prime section. What's new probably is just using the first derivative test to justify our answer. So what we would say is f of x has a local max at x equals negative 2 because f prime of x changes from positive to negative at x equals negative 2. So that would be our justification. Now, on the other hand, I notice that at 2, I change from negative to positive, so I can also say that f of x has a local minimum at x equals 2. And again, we're going to justify using that derivative test because f prime of x changes from negative to positive at x equals 2. So that's finding our local extreme values and justifying using the first derivative test. Now, it did ask us to identify any absolute extrema. But if I look at this behavior, I know it starts off increasing and then decreasing and then increasing. So it's pretty obvious there's going to be no absolute extrema in this case. I have my local max and my local min, but we would say, and I'm going to squeeze it in at the bottom here, so sorry about that. We'd say no absolute extrema. And again, we know that because of the behavior of our curve. Okay, so let's do one more. Again, same test here. Actually, let's skip this one because I don't want us to get caught up in the details of the function. I just want us to know how the test works. So we'll skip 2 for now, and we can take a look at that tomorrow in class. So that's everything you need to know for the first derivative test. So then the last piece of this is just what we call the second derivative test. And as you can imagine, it's going to involve using the second derivative as well as the first. So here's how this goes. So it says if f prime of c equals 0, right? So in other words, I know I have a critical point there, or a horizontal tangent. And f double prime of c is greater than 0. So what that tells me is that at c, my function is concave up. Then what we can say is f has a local minimum at x equals c. And graphically, really, here's why. So we said f prime of c equals 0, so I should have a horizontal tangent at c. And f double prime of c was greater than 0, which we said meant concave up. So here's what it looks like. Here's my point C. Right? So then looking at this graph, if I'm concave up, that value here has to be a local min. On the other hand, if my derivative at c is equal to 0 and f double prime of c is less than 0, meaning that I'm concave down at C, then that must mean that F has a local max at x equals C. And again, graphically what we're looking at is something like this. At C here, I have a horizontal tangent. That derivative is 0. And I know my function is concave down, so that makes this value a local max. So that's the second derivative test. So here's how we apply the second derivative test. Okay, it's going to ask us to find local extreme values of f of x, so our local max or local min values, and then justify our answer using the second derivative test. So now I know I need to calculate a couple of things. First, I need to find the first derivative and find the points where it's equal to 0. And then I need to plug those critical points into the second derivative to determine if the sign is positive or negative. So here we go. Let's first find the derivative of f of x, which is 3x squared minus 12. All right, this function is looking familiar. So if I factor, I get this. That's a difference of squares, so I can factor that. And I know I have two critical points, one at -2 and one at 2. So that's the first piece. Now I know where f prime of c is equal to 0. So now we have to look at the second derivative piece of this. So my second derivative, f double prime of x, is just 6x. So now I'm going to test each one of my critical points here. So first, if I plug in f double prime of -2, we get 6 times -2, which is -12, which is less than 0. So I know at that point, my second derivative is less than 0, so I'm concave down, meaning I have a local max. Now, again, if I test my second critical point, I'm plugging in the second derivative to find about the concavity there. Now I have 6 times 2, which is 12, which is greater than 0. So now I'm concave up, which gives me a local min. So that's the work we would show. Now we actually have to justify our answer. And remember, this is not enough for justification. They want to see you write this out and explain it. So what we would say is that f of x has a max at x equals -2 because, now we have two pieces to this, because f prime of -2 is equal to 0 and f double prime of -2 is less than 0. So we've kind of stated both of those conditions of our second derivative test. Then on the other hand, we could say f of x has a min at x equals +2 because f prime of 2 is equal to 0 and f double prime of 2 is greater than 0. And if we compared this, right, to problem number 1 of the first derivative test, right, it was the same function, we got the same result, we just used different information to get that result. So that's all there is to the second derivative test. So again, I'm going to leave that second example off because this is a pretty straightforward concept. We can look at that second example in class tomorrow if we need to, and then you'll get some more practice with both of these tests.